In 1942, a 12-year-old Hugh Everett III sent a letter to Albert Einstein asking whether the universe was held together by chance or unified by some kind of force. Dear Hugh, there is no such thing as an irresistible force and an immovable body, but there seems to be a very stubborn boy who forced his way victoriously through strange difficulties created by himself for that purpose. Yours sincerely, A. Einstein. And it was 12 years later, in 1954, that this stubborn boy presented what would be his only contribution to theoretical physics during a late-night drinking session, reflecting on the ridiculous things about the nature of quantum mechanics. His aim was to tackle the measurement problem head-on. The Copenhagen interpretation is terribly incomplete because of its previous dependence on classical physics, as well as being a philosophical monstrosity with a concept of reality for the macroscopic world and a denial of the same for the microcosm. In fact, as we have seen, the Copenhagen interpretation depended on this so-called Heisenberg cut, the arbitrary line between the micro and the macro, which kept the more bizarre aspects of the quantum world at bay. Everett rejected this. He threw the notion of wave function collapse out of the window. Let's start by thinking about an experiment in a laboratory. Traditionally, the experimenter is distinct from their apparatus. They can influence the experiment by adjusting the temperature or the magnetic field, but they are only an observer, not part of what is being experimented on. Everett realized, however, that this cannot be correct. The experiment is made up of electrons and nuclei, each described by individual wave functions. In terms of quantum mechanics, this experiment is a superposition of all its wave functions, and so is the experimenter. To fully describe the laboratory, we need to consider the superposition of the experiment and the experimenter. The whole laboratory is the superposition of all the particles inside it. But if the experimenter is now coupled to the experiment through superposition, where is the collapse? The problems only get worse from here. Everett realized that the experimental laboratory is not isolated, but is part of the universe. The total wave function, the universal wave function, must encode the properties of every particle in the universe. Within this universal wave function are all the particles that make you up, and, as in all quantum mechanics, the Schrödinger equation moves the universal wave function into the future. But if this is the case, where is the probabilistic aspect of quantum mechanics? Everett proposed that the universal wave function encodes more than just our universe. It also encodes all possible universes as a superposition of universal wave functions. Within these universes, an electron would be in a two-state assumption, but the act of observing the electron cuts through this assumption. The coherence between nearby universes is broken by observation, and all universes follow. In some universes, the electron is definitely found in state A. In others, it is definitely found in state B. And remember, you're in the universal wave function, so you, in some universes, measure the electron in the A state, and you, in other universes, measure the electron in the B state. Effectively, two separate universes have become distinct within the universal wave function. And this would happen in every quantum measurement, in every quantum interaction. Every probabilistic outcome in quantum mechanics is played out within the superposition of universal wave functions. Individual universes with distinct futures crystallize from the final superposition. In the many worlds theory, other universes are just as real as ours, and in some of them, there are other versions of you. In nearby universes that maintain coherence, these other versions of you are almost identical to the one you are experiencing. But in another universe, a little further away in the mix and distinctly separate from ours, you are very different. In others, you don't exist at all. This sounds a lot like the Level 1 multiverse, with parallel worlds unfolding. But in reality, in the Level 3 multiverse, each branching universe can be its own Level 1 or even Level 2 multiverse. Infinities upon infinities and more worlds beyond worlds. From Young's apparently simple double experiment, we arrive at what Max Tegmark calls a level 3 multiverse. By eliminating the need for the wave function to collapse, we end up with an infinite sea of parallel universes. Some physicists dismiss many worlds out of hand, calling it excessively wasteful. Nobel Prize winner Girard went so far as to say that there would be a stupendous number of parallel worlds, which are only there because physicists haven't been able to decide which one is real. And indeed, Everett's insights were largely ignored during his lifetime. After getting the cold shoulder from much of the physics community and Niels Bohr himself, he left physics after completing his doctorate, going to work as a computer programmer and dying of a heart attack at the age of just 51. What happens to you that makes you you as the individual universes diverge? Are there two distinct versions of you, each now imprinted with the memories and experiences before the split? Let's say you have a coin, a perfectly fair coin, with equal chances of coming up heads or tails. The stakes when you toss that coin are high. Tails, you're executed. Heads, you survive. As the coin spins in the air, you know that the outcome is 50-50. The coin lands and settles on heads. You breathe a sigh of relief, but are instructed to toss the coin again and again and again. You realize that this is a game you are destined to lose. You'd have to be very lucky to keep getting heads on every toss, so your execution awaits. Around you it seems obvious. You are surrounded by things, some solid, some liquid, and some as ethereal as air. But have you ever stopped to think that all this reality could be an illusion? If you look closely, everything is made up of atoms, combined into various molecules. And we can dismantle reality even further. Atoms are broken down into smaller particles, such as electrons and quarks. Do these fundamental particles represent reality in its purest form? Not exactly, because we also need to consider how these particles interact through fundamental forces. All of this is written in the language of mathematics, numbers and equations that describe what we see and feel. But an intriguing question arises. Where do these rules of reality, written in mathematical language, actually exist? It may seem a strange question, but where could these rules exist? This is where we come to Max Tegmark's Level 4 multiverse. This multiverse is filled only with mathematical structures, encompassing the entire realm of possibility. These mathematical structures can encode every kind of universe within this Level 4 multiverse. Here, we find the definitive set of all reality and much more. In fact, this theory has many similarities with the simulation hypothesis, which suggests that our reality is nothing more than a super powerful program in a computer. A computer in a universe above our own, with programs written by beings for whom we are mere toys. But the Level 4 multiverse proposed by Tegmark would be more than just a physical computer. It would be an existence composed only of mathematics. And so, theory after theory, we reach the ultimate vision of the multiverse. We began our journey by looking beyond the horizon and wondering what lay beyond. Now, we find ourselves questioning the meaning of reality and our own existence. Of course, the multiverse is not a single concept. It's more like a mixture of ideas, some based on solid science, others almost science fiction. For some physicists, the multiverse seems inevitable. Ideas like eternal inflation are simply too attractive to be wrong. Other physicists are sure that they are on the right track with string theory and the existence of the string theory landscape. Even the seemingly simple idea of reflecting on dark energy and our cosmic horizon implies some kind of multiverse. But some still vehemently oppose the notion. For them, talking about multiverses that are forever beyond our reach is anti-scientific. Ideas, they say, are only scientific if they can be examined scientifically. Therefore, parallel universes that will never be visible through telescopes or microscopes should be excluded from science. But in reality, our ideas about the multiverse are still too early in their development to question their scientific validity. And the mathematical structures of Tegmark's Level 4 multiverse, for the time being, are little more than a dream. This doesn't mean that the multiverse will be forever inaccessible. With enough mathematical effort, we might find a loophole to parallel worlds. We may find complex space-time structures, similar to the idea of wormholes, which will bring the invisible into view. Some have suggested that patterns may be written in the sky, in the cosmic microwave background. They claim that these could be traces of universal collisions in the many dimensions of string theory. The search continues, but for now, contact with or evidence of these alternative worlds is little more than wishful thinking. We have no idea how theories will be developed in the future, and we simply don't know if the multiverse will ever be glimpsed by our telescopes or experimented with in our laboratories. In reality, the multiverse may be forever hidden in the mist. Don't forget to like and subscribe. Leave a comment to let us know what you think. Thanks for watching and see you next time.